Hello everyone, I'm Jianhao from Nanjing University. Today, I'm going to share our work, Silent Bugs Matter, a study of compiler-introduced security bugs. This is a collaborative effort between Nanjing University, University of Minnesota, and the EPFL. This study paper focuses on the gap between compiler correctness and security. Let's start with two code examples. The first code snippet is a security check attempting to protect against an integer overflow. From the security perspective, the check is necessary to prevent uncontrollable integer overflow. However, from the correctness perspective, the compiler assumes there is no undefined behavior in code and thus can eliminate the check. The second code snippet is where a programmer attempts to scrap the sensitive data saved on stack with a memory set. Therefore, from the security perspective, the memory set is necessary. However, from the compiler perspective, as the secret buffer would not be used afterwards anymore, this memory set is a data store and can be removed to improve performance. These two are typical examples that show compiler correctness does not equal security. To describe bugs in the scope of correctness security gap, we introduce the term compiler-introduced security bugs, or CISB. A CISB is a software bug whose source code is secure to execute with an ideal interpreter, but the compiled binary code becomes insecure on the target environment. We use the term introduce to describe that security issues in the code are created during compilation, not in the source code itself. Please note that this term is neutral and does not assign responsibilities for the bugs. CISBs are widespread and possibly exploitable. People debate a lot about CISBs while they have not been comprehensively studied. This lack of understanding has turned CISB into somewhat of an urban legend, where people may have heard about them, but lack clear insights. To shed light on the nature and impacts of CISB, our research aims to study them in the real world. Our research explores three aspects of CISB: the bugs themselves, about the root causes and impacts, programmers about their knowledge and views, and mitigations about risks and challenges. First is the bugs themselves. To study CISB, we aim to gather real-world examples and build the first CISB dataset. Our approach involved collecting data from two data sources. First, the bug reports from compiler Bugzillas, the platform where programmers globally report CISB, and the patch history of the Linux kernel, the most well-known open source program. Despite the potential richness of this data source, we still have to overcome many challenges, such as the vast number of unrelated bug reports, diverse opinions, and even errors in human-written bug reports, and the lack of an accepted definition of CISB before. To address these challenges, we use keyword intersection strategy to select the most relevant bug reports and use correlation analysis to correct missing or inaccurate information. However, due to the diversity of bug reports and the piecemeal nature of CISB bug itself, human effort remained essential. In fact, we spent more than 1,500 human hours in collecting, confirming, and reproducing the CISBs. In the end, our effort resulted in a dataset containing 120 real-world CISBs with 48 unique bugs. With these collected bugs, we summarize a taxonomy of CISB based on their root causes, formation, and the security impacts. We identify two kinds of root causes. First, implicit specifications. Language specifications define some unacceptable code behaviors and allow compilers to make assumptions about them. When programmers use such code behaviors, compilers can break the code based on these assumptions. The most common example is compilers' assumption of no undefined behaviors, such as the first code example we have showed before. Second, orthogonal specification cases. Security can exceed the scope of traditional language specifications. Security can depend on code effects that are orthogonal to code semantics. For instance, as the code we showed before, deciding whether data is sensitive or not is not defined in traditional language specifications, and compilers may not preserve the boundaries of sensitive data during compilation. We further classify CISB based on the involved compiler behaviors and the impacts of the bugs. For implicit specification cases, bugs can be divided by how the compiler modifies the security code semantics. Compilers can eliminate, reorder, or reconstruct security code, leading to semantic-related security impacts such as logic errors or memory corruption bugs. For orthogonal specification cases, bugs can be divided by the kind of security properties broken by compilers, such as the boundary of sensitive data or the execution time equivalence of crypto code. Their security impacts depends on the specific orthogonal scenarios. For more details about the root causes and taxonomy of CISB, please refer to our paper. Okay, we have many interesting findings about CISBs. First, compilers' assumption of no undefined behavior is still a main fact of CISBs. Second, CISBs are much more diverse than previous studies. Besides undefined behavior, compilers' assumption of default behavior and environment settings can also result in CISB. Furthermore, new attack surface can be impacted since security boundaries are developing faster than language specifications. Finally, we observe a higher incidence of CISB on recent years, and many of these real-world bugs causing serious impacts, such as security check bypassing or information leaks. Okay, our second research question focuses on a user survey. We conducted the survey to get answers about programmers' knowledge and awareness, experience, and views. We included participants from both the academia and industry, including individuals from compiler communities. We also released the use questionnaire. You can find it from this QR code. Here are some interesting findings from our user survey. First, programs' awareness of CISB and undefined behavior is not optimistic. For example, over half of them are not aware of CISBs caused by undefined behaviors. Second, most of programmers feel difficult to learn, debug, or avoid CISBs. Please refer to our paper for more interesting statistics about the user survey. Our final research question is about the mitigations. First, we find it risky to rely on programmers to prevent CISB due to many practical challenges. For example, there are too many undefined behavior rules to remember and understand. Furthermore, compilers can optimize out the prevention of an original CISB because compilers lack awareness of specific security needs and the meanings behind the security patches. Second, using compiler options to disable or prevent compiler optimizations may come with effectiveness and performance trade-offs, and disabling all compiler optimizations may not prevent all CISB. Last but not the least, an automatic prevention method is usually a better option. However, recent works are mostly ad hoc. As an alternative, we propose a more direct focus on security boundaries. In conclusion, our study has made some contributions to the understanding and mitigation suggestions of compiler-introduced security bugs. First, we collect an open source CISB bug dataset and propose a new taxonomy. Second, we study programmers and learn their struggles about CISB. Third, we investigate the risks of existing mitigations and identify the remaining challenges. You can find more information from our paper. That's all of my presentation. Thanks for your listening. I'm happy to take your questions.